Okay, well, welcome to lesson 64. Today we're going to be talking about how to identify, write, and graph inverse variations. I can't wait till we get to the graphing part because we have not so far seen a graph that looks quite like what happens when we have an inverse variation between x and y. One thing that I think is important for us to remember, if we go back to, I think it was lesson 56, where we learned about direct variation, is that direct variation is the relationship between y and x, where y is equal to kx. K, if you remember, is a constant, and it represents the rate of change. If this were an equation for a line, k would be the same as m, the slope, the rate of change. And what we want to understand about direct variation is that in a direct variation relationship, when y increases, x also increases. Okay? So in a direct variation, and you can see it in the multiplication problem, right? Kind of no matter what k is here, if x gets bigger, the product of those two numbers is going to make it result in y also being bigger. So direct variation is a relationship where if x increases, y increases, or if y increases, x increases. It's what we see in the slope of a line, right? So if we can just sort of visualize that, here's my coordinate plane. If I've got a line here, and that would just be, if this were going straight to the origin, if I had drawn that perfectly, this would be the line y equals x, right? And we can see that where my x increases, my y also increases, and it's the same on the other direction. Where my x decreases, my y decreases. That's called a direct variation. Now, an inverse variation is the opposite of that, and that's what we get to explore today. And don't lose heart, guys, today in this lesson. It might feel a little confusing in the beginning, but stick with it, okay? Stay engaged, and let's see if we can't reason our way through what it means when y and x are not directly related, but inversely vary with one another. Okay, so here we go. The equation, not y equals kx, but when xy equals k, or when y equals k over x, which is what would happen if I were to solve this for y, right? If I took the x and I divided it out and I put it over here. So these are both the same relationships here, where k is a non-zero constant. This equation right here, or this one, remember they're equal, just a different way to write the same thing, defines an inverse variation between x and y. And here's what's happening, okay? Here's what's happening. In this equation, or this equation, either one, if x gets bigger, y has to get smaller in order for k to stay the same. Remember, k is your constant. It's your rate of change, it's your slope. In a line, it's m, okay? So don't let that get too confusing. Just try to tuck that away into your brains, and we'll bring that up here later as it becomes more relevant. But in any case, if k is to stay the same, which it must because it's a constant, in an inverse relationship, an inverse variation between x and y, when one of these variables gets bigger, the other one has to get smaller in order for this value to stay constant. Okay, let me show you what I mean by that. Okay, let's pretend instead of having a line here, okay, let's go ahead and model this. And Mrs. Fairbank used 5 colors for this. So why don't you, maybe Mrs. Bryden can push pause on the video and you guys can get some colors out. If you don't have 5 colors, no big deal. Honestly, 2, maybe 3, and if you don't have any, that's okay too. You can do it with a normal pencil, but let's push pause just for a second. Make sure you've got some colored pencils, and then we'll move on to the next exercise. Okay, so if she pushed pause, and now we are moving into seeing what this looks like, okay, in terms of geometry, we might understand that x times y remember up here, here's x and here's y, is the same formula, let's say, as finding the area of a rectangle, right? If this is length and this is width, then this would give me area, where area in this case would be the same as k, all right? So let's just model this out. And the other thing that we're gonna do, that you might wanna do right now, is just unclip your binder. You're gonna need the next page, and this is a long lesson, okay? We're gonna need to see this, we're gonna complete this table as we go. So I'm just gonna be moving this paper in and out as we go. All right, guys, here we go. So we're gonna pretend like x is our length and y is our width, and we're gonna find area. I'm gonna start with a red pencil. Let's say that we always want the area of our rectangle to equal 16. Okay, we always want it to equal 16. So in our case, x times y is going to equal 16. That's going to be our area. So that means that if our x value right there, our width is 1 square, let's see, I'm going to make sure that I can go 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, I can. Easy. All right, so in that case, I'm going to start right here. Okay? 1. If x is 1 and I want the area to be 16, then that means that that my length here needs to be 16 units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's going to stop right there. All right? And I'm going to go ahead and say there is if x is 1. Oops, I went a little too far. Will you do that better than I do? Then we can see here that where x is 1, y has to be 16 in order for the area of my rectangle to equal 16. Okay? So you've got that here in your table where x is 1, y is 16. Now let's go ahead and put some other values in here. I'm just going to choose some. So let's make the width 2. Now remember, the area is always going to say 16. So if the width is 2, then the length has to be what? 8, right? Because x times y equals area. So let's go ahead and model that now on our little chart here. I'm going to use a yellow. You use whatever you want. Okay, but let's make x is now 2. So to make this 16 units, my length is going to now be 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to stop right there. Okay. Now that is the same number of units. That's what we were going for, right? But when x got bigger, right? X was 1 here, now x is 2. Y has to get smaller in order to maintain that same number of units. Again, that's called an inverse variation. Okay, let's try another value. Let's go ahead and put 4 in here. If x becomes 4, then my length needs to be 4, because remember, length times width is equal to my area. So here's now, let's go ahead and model that in our chart. I'm going to choose a green. You choose whatever you want. And again, if you're just doing this with pencil, that's also fine. But if my x becomes 4 units, then my y value can also, 1, 2, 3, 4, is going to be 4 units. All right? Because we want the area to stay 16 units. That's my constant. And there are 16 units in there, just arranged a little bit differently. All right, let's do 2 more. Let's this time make the width 8. If the width is 8, then the length, right, my y value is going to be 2 in order to maintain 16 total units. I think I'm going to go with an orange this time. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2. Oops. Sorry, guys. I'm sure you'll be better at this than me. Okay. And then I've got one final box to draw here. Let's go ahead and make x1, in which case obviously the length is going to be 16. Okay? The width is 1. Well, goodness sake. Oh, let's not do it that way. I visualized that backwards. Sorry. Let's make the width 16, which means I'm going to have to turn my paper, probably, in which case the length is only going to be 1. I think I'll do it over here on the side. If my width is going to be 16 units, okay, 16 units, and I'm going to go ahead and use this blue here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I count that out right? Let me just do that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 to here. Hopefully I did that right. Then my y value is only a single unit. So I get something that looks like this. Okay. All right. Now that we have done all of that work, let's analyze it a little bit. All right, so let's write some words here to just discuss, talk about what just happened. Oh, I can see, guys, you probably didn't see that whole chart, did you? Let me just move that up for a second. You should have something on your paper that looks like that. And again, we're just trying to get a visualization of what's happening with an inverse variation between x and y. Meaning, one more time, that if x gets bigger, y has to get smaller in order for, in this case we used area, but we're going to use the letter k to help us remember that it's a constant. In a linear function, when we draw a line like this, it refers to the slope. In this case, we used area. And we can see that as one of those variables gets bigger, the other has to get smaller in order to maintain a constant number of units, in this case 16, which we modeled here also in our table. So let's put some words now to to discuss these concepts that we're learning. Okay, so what happens to the length of each rectangle as the width increases? So let's write a nice sentence here, okay? As the width increases, the length decreases. That's what's happening. Inverse variation. Okay? What will the product xy always equal? What did x times y always equal? It was a constant. That's our k value. In this case, it's representing area. Always represented 16 units. So if we're going to write an equation solved for y to show this relationship, okay, so we understood that x times y equals 16, okay, x times y equals 16, then if we solve this equation for y, meaning we have y on one side of the equation, I'm going to divide by x on this side and divide by x on this side, and I will get y equals 16 over x. Okay, y equals 16 over x. Now, in a direct variation, y is equal to the product of the constant variation k and x. So in a direct variation, and maybe I should do this with colors, I don't know, if it's helpful for you guys, direct variation, y equals kx. However, and this is what we just saw right here, however, in an inverse variation, okay, in an inverse variation, here are the words I want to highlight. Y equals k over x. Here's k, there's the constant, over x. They're different equations. So now, okay, with that knowledge, that understanding in our brains, we're going to analyze and identify whether each one of these four equations is an inverse or a direct variation. If it's inverse, it's going to be y equals k over x, or we could write this two different ways, okay, so just be careful. This could be y equals k over x, or it could be xy equals k. These are the same. In a direct variation, okay, y equals kx. That's what we need to look for. In order to see the relationships, we need to solve each one of these 4 equations for y. Okay, so in this case, I'm going to write this the other direction because my brain likes to read from left to right, so it's easier for me to see 36 over y equals x. Okay, so I just rewrote the equation. I haven't changed it yet. If I want to write this in terms where I don't want y in the denominator, then I could multiply this, right, by y to get rid of it, the y on this side, and I can multiply this side by y, and I end up with 36 equals xy. Which one of these equations does that look like? Inverse or direct? Hopefully you can see it here, xy equals k, that's what we've got. 36 equals xy. If we wanted to, we could divide this side by x and this side by x so that we get y equals 36 over x. This is the same exact equation, you guys, just written different ways, so that I get y equals k over x. In any case, whether it's this way that you see it or this way that you see it, the answer is inverse. This is an inverse variation. Okay, let's take a look at the next one. Okay, so I'm going to rewrite this one also just because I don't love how this looks. So it's easier for me to see it this way. Okay, I want to solve for y. So in order to get y by itself, I need to multiply this side by 12, get rid of it over here, and multiply this side by 12. And I end up with y equals 12x. This is in the form y equals k, which is the constant, times x. Y equals kx. Which one of these equations is y equals kx, and what is it related to? We see it? Y equals 12x is representative of a direct variation. Direct variation, that's going to be a line with a steep slope, a slope of 12. All right, so that's our black diamond line right there. Let's take a look at the next one. The next one's actually a little bit trickier. So if you checked out at any time here, check back in right now, all right, with your mind. Here we go. If we want to write this in terms of y, then we would need to divide by 4 in order to get y by itself, and I end up with y equals, and I can see this as x over 4, which is fine, or I can see it, if it's easier for me, to see it as 1/4 x. Those are the same thing. Okay, so in this case, guys, I've got y equals 1/4 k is a fraction. That's okay. That's all right. This is a constant. This is going to stay the same. So in essence, this is in the form y equals kx, which means it's a direct variation. When one variable increases, the other variable increases. Or when that variable decreases, then the other one decreases. That's not the case here. In this case, when one variable increases, the other will decrease. Okay, that's the difference between these types of relationships between variables. Okay, one more to go. Let's solve this one for y. In order to solve this one for y, I'm going to go ahead and do it in 2 steps. Some of you are probably seeing that you could just divide this whole thing by 3x and this by 3x, which is true, but I'm going to do it one step at a time to hopefully make it easier to see that if I divide this side by 3 and this side by 3, I can do this one step at a time. That gets rid of this, and I end up with xy equals 3, because 9 divided by 3 is 3. Now, if I want, I should be able to see what kind of relationship this is right away. Remember? Because an inverse variation can be represented by either of these equations. These are the same equation, just in different forms. So I can see immediately that this is an inverse variation, where here's y, here's x, and here's k, the constant. If I want to see this in the form y equals k over x, I would divide by x on this side, I would divide by x on this side, and I would get y equals 3 over x. That's y equals k over x. Okay, so that both of these, again, both of these equations are the same equation in a different form, and each one tells us that we are dealing with an inverse relationship. Okay, fantastic. An inverse variation between variables. Let's keep going. All right, so we did this, did our chart, we did this guy. Now we're on to using the product rule to solve an inverse variation. I think this actually gets a little bit easier. If we've gotten this far and you're still with me, okay, then I think you're going to fly through this part. Okay, this particular equation is super simple, and that is this: if you are if we are using a direct variation here, did I skip anything in your notes? No, I guess not. Okay. Hold on, I just want to make sure. Yeah, all right. If y varies inversely with x, then we can use the product rule to find the solution of an inverse variation. And here is how it works, okay? Here's how it works. x1, y1 is going to be equal to x2, y2 in this way, okay? And I know you've got commas, you got a comma here and you don't have it here. Let's just rewrite it this way. So where you have two values, okay, an x value and a y value, and you've got another set of values, one for x and one for y, if they're inversely related, then x1 times y1 will be equal to x2 times y2. And that's because in an inverse variation, in an inverse relationship between variables, the constant has to stay the same. Remember that, guys, from this? We saw it here, back here in your table, right? So if this were x1, y1, x and y, 1 times 16, equals the same, right? The same k value as x2 times y2, 2 times 8. We could set those equal to each other. 1 times 16 is equal to 2 times 8. We could do it with any of those values. So that's how we understand how this relationship is formed. Now, watch how simple it is when we actually put it into practice. If y varies inversely as x, and y equals 5 when x equals 12, then find x when y equals 3. All right, here's my x1, and here's my y1. Okay, so when x equals 12, y equals 5. That's what they just told me. So 12 times 5 should be equal to, and there's asking me to find x. This is x2. When y2 equals 3. So I don't know what x2 is yet. Here's x2 when y equals 3. I could simplify this to say 60 equals 3x. Divide by 3. And understand that when y equals 3, x is going to equal 20. Okay, when y equals 3, x equals 20. I feel like that's quite a bit simpler than what it looked like. Hopefully you feel that same way. Let's try it again for the next one. Okay, so again, we remember here's our equation at x1, y1 equals x2, y2. The product of x1 and y1 has got to be equal to the product of x2 and y2. So let's figure out where x1 and y1 are. If y varies inversely as x, this only works, guys, in an inverse variation, okay? And y equals 3.5 when x equals 20. All right, there's the first one. So here's my x1, here's my y1. So when x1 is 20, y1 is 3.5. So 20 times 3.5 is going to equal, it says find x, so I don't know what x2 is yet. But I know that y2 is 10. So 20 times 3.5, okay, if you want to do that with a calculator, you can. If you want to do it in your head, either way, you should end up with 70 as the product of 20 times 3.5 equals 10x. So what does x equal then? We're going to divide by 10, and we end up with 7 equals x. That's it. Okay, so those were our answers. All right. If it's a help to you, you can remember that the word direct for direct variation and divide have 6 letters, and division is used to find the constant. In the words inverse and product each have 7 letters, and multiplication is used to find the constant in an inverse variation. So if that's a help to you, then take it. If it's more confusing, then don't worry about it. Just make sure you get the process right and the calculations will follow. let's talk about what I think is the coolest part of this relationship. So far, guys, we have only been graphing what are direct variations. That is, remember this from the first page? Straight lines. An inverse variation, however, does not look like a straight line. Okay? In a direct variation, if there's at least one known value for an x and a y pair, then the constant variation k can be determined. The same holds true for an inverse variation. However, the graph is going to look different. If at least one known value for an x and y pair exists, then the constant of variation can be determined. And that's because our inverse variation, remember our equations are xy equals k, or y equals k over x. So what they're basically saying is if you know what x and y are, you can find k. If you know what x and y are, you can find k. You only need to know one point on the graph of an inverse variation to determine the equation. Okay? So we're going to write an inverse variation relating, this should be an x, not a 2. Please fix that. Relating x and y when x is 2 and y is 6. Then we will graph the relationship. All right, so let's see what happens when we start to fill in some values for x and y, and I'm just going to choose them arbitrarily, okay? And then we'll see what it looks like when we graph these. So again, k equals xy or xy equals k, we know that, right? And we've got our first value for x and y. All right, so k is going to equal, I need to know what k is. K is going to equal 2, that's my x value, times 6, which is my y value. So k equals 12. Once I know that x times y has to equal 12, then I can fill in this entire chart. All right, so let's say that x equals, and this is going to be tricky. I'm going to give you a tricky one to start with. If x equals 0, what does y equal? Okay, if x equals 0, this is the hardest one of all. Look back at our original equation. Here, right here, this form. If x equals 0, if I put a 0 in this denominator, we should know immediately dividing by 0 in math is illegal. It's impossible. It does not work. Whenever we have a 0 in the denominator, we call that undefined. What that's going to look like on a graph, I'll show you. It means that it's never, if x is 0, y cannot hit the y. We have no value for y. I'll show you what that looks like when we get to the graphing part of it. For now, let's keep going with our values. So if x is 1 in this equation, remember, 1 times what is going to equal 12, because k is 12. Okay, k is 12. If x is 1, then y has to equal 12, because 1 times 12 is 12. If x is 2, 2 times what equals 12? 2 times 6 equals 12. If if x is 3, y has to be 4, because 3 times 4 equals 12. Remember, this inverse variation, that means k stays constant. And you can tell from what's going on here that as x increases, y is decreasing. So there's that inverse relationship. If x equals 4, y is going to equal 3. If x equals 12, y equals 1. And if x equals, let's go this far. Let's say x equals 24. Remember, this whole thing has to equal 12. X times y has to equal 12. So if x is 24, then I have to multiply it by 1/2 to get 12. Okay, now that we've got that, we understand how that works. Let's go ahead and turn the page. And you might need to look back on this, might need to look back there on that page in order to see those values. And we're going to go ahead and plot these points. Now I recognize here on your graph that I'm going to move this, okay, so that it's easier to see. Here's your x-axis. Okay, and here's your y. I'm just going to go ahead and color it so you can see it because they didn't quite line up. So just pretend like this isn't here. All right? All right.